Oh, hi. Didn't see you there. I'm Mr. French, your AP Stats teacher. I'm here in my workshop today because I'm going to be using some of my tools to show you what a goodness of fit test looks like for a chi-square test statistic. So we're going to do a whole entire test statistic test for a chi-square goodness of fit test. This is what we're going to do. I'm going to use this block of wood to make a six-sided die. So it'll be a handmade six-sided die. And we are going to compare that with what a true six-sided die would do. So let's think about a few things. A six-sided die has six sides, and if it's a fair die, each number should have a 1/6 chance of showing up. If I make my own six-sided die, we should assume that if it's completely fair, each number has a 1/6 chance of showing up, unless the data shows otherwise. And that's what we're going to test today. But in order for me to make a six-sided die out of this big block of wood, we're going to have to get the bigger tools out. Come on. So I got my six-sided die right here. This is brand new, handmade six-sided die. What we're going to do with a goodness of fit test is we are first going to assume that this is a true, fair six-sided die. Now, what should we expect if this is a fair six-sided die? We will assume the distribution is universal at 1/6 until we have data to support otherwise. So I'm going to number these faces 1 to 6. I'm going to throw it 40 times, and we're going to carry out a full chi-squared goodness of fit test. So let's start rolling it. 4, 3, 6, 4, 2, 2, 6, 3, 6, 3, 2, 5. Woo! That's 2. 2. That's 1. 5. 2. 6. 2. 2. 5. 4. 3. 4. 1. 6. 6. 2. 5. 1. 2. 1. 5. 5. 4. So that is 40 throws with this die, and we're going to test to see how good does it match against a regular fair six-sided die. So was I able to make a six-sided die that is fair? How well does it stand the test? The goodness of fit test. Here we go, chi-square, here we go. Here we go, chi-square, here we go. Welcome, let's do this. We just got some data. what I'm going to do is I'm going to tell you what our goals are for this lesson. We're going to use the data from the created six-sided die scenario, and then we'll look at another scenario, and we'll crack through our goals here. So, oh boy, here we go. We are going to be doing the following. So this is 11.1, day 2, and it's chi-square goodness of fit testing. In the last video, we really just went over how the test statistic is calculated. We looked at where you get the p-value from and how you collect the degrees of freedom, or how you find the degrees of freedom. In this one, we're going to put all those things together, and we're going to do a full significance test for a chi-squared goodness of fit test. This will follow the 4-step process, but before we get started, we're going to talk about our goals. So goal number 1 for this lesson is to perform a chi-square test for goodness of fit. And then the second thing that we'll do is we're going to conduct a follow-up analysis when the results of the test are statistically significant. So let's go ahead and carry out a test. So we're going to do a test for the DICE data. This will follow the 4-step process. So let's go over our state. Here is the statement that we should make. We have a null hypothesis, and the null hypothesis is that the wooden die number distribution is equally distributed amongst all numbers. And then alternatively, the wooden die number distribution, here we go, is not equally distributed amongst all numbers. And this is kind of nice because usually in a significance test we have some sort of parameter or like a symbol, and we have to define it, but really in the context of this we don't have to do any defining because it's all here, which is great. So that is our statement for this particular test. Okay, now we're going to go to the plan, and this is new. We did not go over the plan or the conditions in the previous one, so this is big moment. This is a big moment, okay? This is a really big moment for you folks. The conditions for a goodness of fit test. Actually, if you looked at the backside of the textbook, it has all the conditions there for you. Okay, so feel free to check that out sometime. The conditions for this test are, you know it, you love it, random. Oh yeah, the numbers were randomly generated because I was throwing a die. I was just tossing the die. There was no technique. Totally random. So we're good to go. The next one, you know it, you love it, 10%. Now in this case here, the 10% condition is certainly met. Think about that for a second or two. Are we sampling more than 10% of the population each time? So our sample size, remember, is 40. Did we sample too large? We have a sample size of 40. The answer is no, we didn't sample too much out of the population, because guess what? The population of dice rolls is infinite. We can keep rolling the die, rolling the 6-sided die forever and ever and ever. Huge one, large counts. Okay, here we go. The large counts condition. This is a big one. So the large counts for a goodness of fit test is all expected counts need to be at least 5. If the true distribution is 1/6, so each number should show up 1/6 at a time, I'm going to check this. I'm going to say, well, our sample size was 40, and I'm going to times that by 1/6. Okay, this is what we would expect to happen. So it turns out all numbers in this case here for the dice will all have the same expected count, because a die we are assuming is universally distributed. And this number here is 6.667. And since all of them have this, so all expected counts are 6.667. Now we haven't talked if that meets it or not, but it certainly does. With a goodness of fit test, all expected counts need to be at least 5. So in this case here, all expected counts are 6.67, which is greater than 5. So we are good to go. Make sure all your expected counts are greater than 5. We're going to take a look at some of the raw data here. So this is the data from the dice rolling. So I had all these numbers show up, and then I counted the number of times each number showed up. So 1 showed up 4 times. Its frequency was 4.
2's frequency was 11, 3's frequency was 4, 4's frequency was 6, 5's frequency was 7, and 6's frequency was 8. So this is the data. Remember, these are all of the observed counts. Usually, you don't have to do this part for the do step. You'd already have this. So the do step, you could just go ahead and start doing your calculations. So a few reminders about the do step. So for the do step, we're going to say chi-square for goodness of fit. I just wanted to put the title of the test somewhere. I'm going to go to my handy dandy formula sheet if you forgot it. It's right here. Chi-squared test statistic in general. It's right here. Hopefully when I edit this I can just zoom in. It's the observed minus expected squared over the expected. And we're going to add those all up. So I'm going to write it out here. So x squared equals, so observed minus expected. So I'm going to start with the first one here. So the observed count for the number 1 was 4, minus its expected, which we've already calculated. If they all have a 1/6 chance, 1/6 of 40 is 6.667. You square that difference and you divide it by the expected, 6.667. And then you add that to the next one. So 2 showed up 11 times. So it's going to be 2 minus 6.667 squared over 6.667. What's the thing we have to remember if we don't want to write it all out? That dot, dot, dot. Now you could write all of them out. It's fine, but it's a waste of time. You have to put the dot, dot, dot though. If you do not put the dot, 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 it's implying that you're done with your calculation and you'll lose credit. Dot, dot, dot means that like the greater I or the greater is going to get the idea. So if you don't want to do all of this, what you can do is, what you can do is use your calculator. So your calculator, go to stat, edit. Oh, I got some data in there already. So I'm going to put my observed into L1. Oops. So I have my observed and expected. I'm going to go to stat, over to tests, because we're doing a chi-squared goodness of fit. Now there's 2 chi-squares. Don't go to chi-squared test. That comes in 11.2. We're doing a chi-squared Goff test. Observed in L1, expected L2. Degrees of freedom. So let's state our degrees of freedom. We have degrees of freedom. Remember, that is the number of categories minus 1. In this case, the number of categories is 6. Coincidentally, it's 5 again. And I'm just going to calculate it. Notice how we get our chi-squared statistic at the very, 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 very top. We have a chi-squared value of 5.299, so I'll just say 5.3. We also have a p-value that is equal to 0.38. This is our do step. Make sure that you have the following. You need to have your expression for calculating your test statistic, state the degrees of freedom, and then make sure you have your value for your test statistic and your p-value. Someplace, make sure you put the title of the test that you're doing. I think that'd be helpful. Now we're going to conclude. I mean, it's pretty, this is the 4-step process, baby. We've got a p-value. Since our p-value of 0.38 is greater than alpha equals, I didn't set the alpha level at the beginning. Remember, if that's the case, typically the most common one is 0.05. Since our p-value of 0.38 is greater than alpha of 0.05, we fail to reject the null. We do not have convincing evidence to suggest that my die is unfair. All right, so we failed to reject the null. We have non-convincing evidence. Yeah, so these are not statistically significant. So my die could be fair. That's what we're pretty much saying. We failed to reject the null. What type of error could we have made? Go ahead and touch the screen that you're watching this on. Correct. Nicely done. We have potentially made a type 2. Potentially made a type 2. Potentially made a type 2. So this next example is in your book. It's on page 688. It's about the hockey players. Okay, some context there. Essentially, we have some data on the birthday distribution of professional hockey players. So we've broken up the year into 4 pieces. We have January to March, April to June, July to August, and October to December. Shout out to the, July, August. So this example can be found on page 688. This is our next example here. We're going to be looking at the birthday distribution of a simple random sample of 80 NHL players. So we break up the year into 4 pieces. So we have January to March, April to June, July to September, and October to December. And out of the simple random sample of 80 hockey players in the league, this is how their birthdays were distributed. 32 had birthdays from January to March, 20 had birthdays from April to June, 16 had birthdays from July to September, and 12 had birthdays from October to December. So the question is, or I guess the claim here is that you would think that birthdays are equally distributed. It shouldn't really matter the month that you're in. Like, you would expect that birthdays are equally distributed. And that's actually, in this example here, the claim is that birthdays should be equally distributed. But here we have evidence to suggest that perhaps maybe it's not. Notice how there's so many more here versus here. It looks like kind of like a skew right a little bit with the months. So the question is, does this data provide convincing evidence that the birthdays of hockey players is not equally distributed? So we're going to get to our state. Our null hypothesis is that the birthdays of all NHL players are evenly distributed across the 4 quarters of the year. And I'm a huge fan of alternative hypotheses and a goodness of fit test. Essentially what we're going to be saying is that if the null is that the birthdays are equally distributed, the alternative is that they are not equally distributed. Hello! I'm filming the lesson! So the alternative is that the birthdays of all NHL players are not equally distributed across the 4 quarters of the year. Hi, Ramsey! Hi, Ramsey boy! Woo! Did you hear that we're doing a significance test? Is that why you came down here? There he goes. Gentle giant, Ramsey French. So we'll get to our plan here. So our plan is a chi-square test for goodness of fit. I know I put it in the do part last time. Usually you'd put it in the plan, but it's as long as you mention it, it's going to be fine. So let's go ahead. Random. Yes, it is, because we have a simple random sample was taken from the NHL. So just mention that a simple random sample was taken. Hi.
Hi. How's it going?
It's going really well. How are you? We're live.
You're live. Who is this? What class is this?
AP Stats.
Do a shout out for U.S. history? Hey, those of you in Miss French's U.S. history, you know who you are. Go ahead and check out those Google Slides. Pick out that Google Classroom. You've got some great stuff with World War II as well. So if you need a little brain break from all this great math, you know where to head over.
So let's get back to it. We got the 10% criteria coming up here. We are not sampling with replacements, so we're sampling without replacement. NHL, pretty big league, and the teams are pretty big as well. I would expect that in the entire league of the NHL. So there must be at least 800 players in the entire. Now, you know what? This is the fun part. I don't know if that's true, but our goal was to conduct it, and so I'm just going to assume that that's the case, right? So if it says, does the data provide convincing evidence, I'm going to be very, very, very liberal with a lot of definitions and a lot of assumptions that I'm making. So I'm just going to play silly and assume there's more than 800. Large counts. So large counts. The expected counts need to all be at least 5. So if we have 80 people in our sample and there are 4 quarters that we're looking at, a quarter of 80 is 20. All expected counts are at least 5 because they're 20. Now we got our do step. Time to do that do. All right, so I'm just going to get straight to the calculation here. We have our chi-squared, which is the observed minus expected. So our observed is 32 for this one, and we expect 20. So our observed is 32, the expected count is 20. So 32 minus 20 squared over 20 plus, ooh, perfect match. 20 minus 20 squared over 20 plus dot dot dot. Okay. So now what we're going to do is I'm going to go to my calculator. It's time for the calculator. Time to enter that data. Stat. Here we go. 32, 20, 16, 12. Woo! Fastest calculator in the Northwest. So let's go ahead and go to stat, tests, all the way down to goodness of fit. There it is. Observed L1, expected L2. Degrees of freedom is no longer 5. Remember, it's the categories minus 1. There are 4 categories. It's the number of categories minus 1. There are 4 categories here. So make sure you change your degree of freedom to 3. I'm going to put that here as well. So I'll say degrees of freedom is 3. Calculate. Cool. That was super fast. So we have a chi-squared that's equal to 11.2, and we have a p-value of 0.0107. And that's all we really need. That's great. Calculator to the rescue here. So let's go ahead and conclude. So because our p-value of 0.0107 is less than alpha equals 0.05, we reject the null. We have convincing evidence that the birthdays of NHL players is not evenly distributed across the 4 quarters of the year. Cool. Let's sit back and think about that for a second. So we have evidence to suggest that the birthdays are not equally distributed, which is kind of interesting. So the second bit of this, so the second goal of our lesson for today was to perform a chi-squared test for goodness of fit. Now we have done 2. We have completed 2 significance tests. The second one was conduct a follow-up analysis when the results of the test are statistically significant. Okay, so if we were to conduct a follow-up analysis, the follow-up analysis would be looking at the contributions. Okay. So our contributions are right here. And if I scroll over, I can see all of them. Now what a contribution means is it's the value of each of these. So the first value that I have, this equals 7.2. And it should kind of make sense that this one actually equals 0. Okay. The next one, I believe the contribution for this one, if I were to write it, would have been 0.8. And the contribution for this one was 3.2. So what you do in a follow-up analysis is you just take a look at the contributions and consider like where you'd want to follow up your study. So in this example here, looks like the beginning of the year. So when you have a perfect match, your contribution is 0. When it's further away, it's providing more evidence against the null. So as your chi-squared gets larger, it's more evidence against the null. If you think about the distribution of a chi-squared test statistic, as your chi-squared gets larger, you are observing rare things. So since this is 7.2, it's the largest one, this is providing the most evidence against the null. So we might want to think about, this is January to March. So in the context here, it's from a book by Malcolm Gladwell called Outliers, and he suggests that, typically, if you're born at a certain time throughout the year, it's more likely that you get on it's more likely that you might be ahead in your class. And so as you start playing sports in like middle school and high school, you're more physically developed, and so you're going to excel a little bit more than the people who are of your same grade, but like almost a year younger than you. And so you're caught for more select teams, and that's essentially his argument. And you know, in this particular case, the data does show that it's not an equal distribution. So there is something going on here. So that would be an example of a follow-up analysis by looking at the contributions in your chi-squared test. Goodness of fit. Cool. All right, so what I suggest you practice. I suggest that you practice. The last video was problems 1 through 3. Or sorry, the last video was 1, 3, and 5. That was for 11.1. What I would suggest now, 7, 9, 11, 15, and 17. And 11.1. This is where we're at so far. So 11.1 for each of these. This does end 11.1. We are now going to go into 11.2 on the next few videos. So thanks for being so flexible with all this. I'm going to try my best to keep producing these videos, producing some more content. It's been really fun, and I hope you folks enjoy it and that you're watching these videos and you're reading your textbook. We'll get through this together, and I'm not going to stop. I got to teach AP Stats, so might as well just keep making these videos. So thanks for giving me the opportunity to do so.